All right, kiddos, so we're going to pick up a little bit after we left off. Remember the last video, at least if you're going in order, was molecular representations. We talked about, we had Lewis structures. Obviously, we had a molecular formula. We could draw that out in a Lewis structure where we show where all the electrons and bonds are. We show every atom, all the lone pairs, all that. We then did partially condensed structures where we took those down and sort of condensed where the hydrogens bonded to the carbons. Then we had that was partially condensed. Then we had a fully condensed structure where we could fit everything in on one line together. And then the last thing we talked about were line structures. And line structures are what I like to think of as like the absolute minimalist approach that you can get to a structure that contains all of the information that you actually need to be able to figure out everything that you need to know. You still know in a line structure what everything is, what everything's connected to, where your electrons are, all of those types of things are all part of where the line structures are drawn, even though in some cases they're assumed by some of the rules that we're going to talk about here in this video. So real quick here, the first two rules then are right here, and I put two up at once. I don't normally do that, but I'm going to put two up at once because these two are directly tied together. And we discussed this in the last video, but every endpoint, okay, or every corner is a carbon atom, okay? So carbon, 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 carbon. All right, and that the carbon atoms that are normally in a straight chain are drawn zigzag. So if you just to remind you what I mean by straight chain, if you went back to the say partially condensed structure that we were talking about, we had our four carbons arranged in a line. Okay, that's a straight chain, and so that's going to be the zigzag then that we're going to do. Why do we have to do that? Well, because if I didn't zigzag them, if I just said, hey, you just got to draw a line through where they are. Okay, great, there's my line. How many carbons are there? I don't know. How do I differentiate between the carbons? Well, that's why we draw them in zigzags, because then we get endpoints and we get corners that are going to allow us to know that, hey, that's exactly where the carbon atoms are. Okay, so rule 3, hydrogen atoms bonded to the carbons are not shown. Now, here's what's important here. It is really absolutely vital that you recognize that it's not all hydrogen atoms, that it's hydrogen atoms bonded directly to carbon. So for instance, this hydrogen has to be shown. Why? Well, because it's not bonded to a carbon, it's bonded to an oxygen, so we're still going to show that. But the hydrogen atoms that are bonded to the carbons are understood to be there. And what do I mean by understood to be there? Well, it means that we already know that every carbon is tetravalent, right? That it's got 4 bonds. It's going to form 4 bonds with something unless there's a formal charge on it or something like that, okay? So normally 4. So in the case of this carbon, again, I know there's a carbon there, and I know that I already see 1 bond where it's formed with the next carbon. So this carbon has 1 bond. That means that its other 3 bonds are taken up by hydrogens. We already showed in the last part that we know what's down at this corner here. What's down at that corner is carbon bonded to 3 hydrogens, and then that's going up there to this carbon up here. So that carbon has 4 bonds. When drawing line structures, that is understood. It's understood that you don't need to draw the hydrogens. In fact, if you had to draw the hydrogens, it would sort of defeat the whole purpose of line structures altogether. What we're doing in line structures essentially is getting rid of the carbons and the hydrogens, making everything much more simplistic. Doesn't mean they're not there. They're still there. They're just not shown. It is understood by your rules of drawing line structures that I don't need to show every hydrogen. So what does that mean for this molecule? Well, I know there's 3 here. So I know that there's 1 hydrogen here. How do I know that there's 1 here? Well, because this carbon, there's a carbon right there, right? It's bonded once, twice, 3 times. 1 bond left over gives me 1 hydrogen. There's a carbon here. It's already got 2 bonds. The other 2 are going to hydrogen. Carbon on the end. Carbons on the end almost always have 3 hydrogens unless there's a double bond or some sort of charge thing going on. So that means that there's 1 bond from this carbon going back to the chain, and then 1, 2, 3 hydrogens bonded to it. So we don't show the hydrogens just like we don't show the carbons. That's what gives line structures their simplicity. All right, so rule 4, something that you probably already guessed from the way that we had things drawn anyway, which is we just talked about the fact that you don't draw your carbons and hydrogens. By saying that, what the sort of obvious conclusion to that is that you then must draw everything that is not a carbon or a hydrogen, or specifically everything that's not a carbon and everything that's not a hydrogen bonded to a carbon. In other words, hydrogens that are bonded to something else, as we mentioned before, you have to draw. But everything else that's not a carbon, not a hydrogen, you have to draw. Okay, there's no line structure minimalization for that. You have to draw those things out. Now, we're dealing with organic chemistry. Organic chemistry is the chemistry of carbon. Most everything is going to have a lot of carbon, so that line structure is still going to make things easier. But there are a lot of other what we would call heteroatoms. They're atoms that aren't hydrogens or carbons. So there's definitely going to be a lot of oxygen. There's going to be a lot of nitrogen. There's going to be a fair amount of phosphorus and sulfur and those types of things in our organic molecules. All of those things have to be drawn out. There's no way to minimize that. There's no special lines for that or anything like that. They all get written as their normal elemental symbol. Okay, so for rule 5, we're going to need a different molecule because we got to, what happens when we have double bonds or triple bonds? We didn't have that in the molecule that we had before. So instead, we're going to do a similar but slightly different molecule. We're going to do a 2-butene and a 2-butyne. That doesn't really mean anything to you at this point, but the ene and the ine, the ene means double bonds, the YNE means triple bonds. Those are sort of functional group type stuff, and we'll talk about all that coming up soon. But that's going to give us a molecule that needs a double bond, a molecule that needs a triple bond. So again, I know that it's a 4-carbon. You'll recognize that from the butanol. That was the but part means 4 carbons. So I've still got 4 carbons. So I've still got my same basic structure for the 2-butene. Okay, 1, 2, 3, 4 carbons. And then at the 2-carbon, right here, where I had the alcohol in the previous one, where I had the OH, I've got a double bond starting there. So instead of, really the easiest way to draw it is I've already got my zigzag drawn to represent the single bonds. For a double bond, I draw a second line. Now what that means is that obviously that changes the number of hydrogens that are there. Essentially, and we'll talk a lot more about this later, every time you put in a double bond, you're pulling 2 hydrogens out. But we could still figure out what actually is going on at each point here. This is a CH3, okay? So there's a CH3 here, right? Because I need 3 hydrogens. This, since there's 2 bonds here and 1 here, this carbon only needs 1 more hydrogen. So that becomes a CH. That also becomes a CH, and that becomes a CH3. Now all that stuff in yellow, I wouldn't draw that on my line structure, but I wanted you to see where all of that came from. That would tell me that my formula for 2-butene is C4H8. Okay, that's the molecular formula that I would get for it. So in the case of our 2-butyne, what we're going to need here is I need to draw 3 lines, right? Okay, instead of 2. So why didn't I just draw another line on the other side of that? Well, there's a really good reason why. So this is what a 2-butyne looks like. I'm going to go ahead and draw it, and then I'll explain it to you. So you're like, okay, that doesn't look anything like the last molecule. Well, it really does. Let me tell you why. Because remember that my endpoints are carbons, right? So carbon, 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 4 carbons. And in the middle, bonding these 2 carbons together is a triple bond. Okay? Why didn't you just draw it in the zigzag fashion and put the other thing? Well, there's a really good reason for that. The reason for that is when you put something in a triple bond, it automatically forces this whole structure into a linear shape. And we haven't really talked about shapes that much yet, but that shape matters, okay? And so the fact that a triple bond forces that section of the molecule, or in the case of a pretty small molecule like this, the whole molecule, into a linear shape, that really matters. Now, obviously, that will then affect some other things, right? And remember, again, the yellow isn't part of the actual line diagram there, so let me get rid of that. I don't want anybody getting confused when they're taking notes going, oh, I don't understand. We got these circles in the line diagrams. That's really weird. What does that mean? Okay, they're not there, right? Okay, this is the line diagram. Okay? So what does that mean as far as our hydrogens? Well, again, CH3, ends are usually CH3, not always, but typically. And then these 2 carbons here, since they have a triple bond between them, and then another single bond going off the other side, they don't have any hydrogens. So that means the formula for 2-butyne then, I don't know if you guys can see that. The formula for 2-butyne then would be C3H6. Again, we added another bond in, and every time you add another bond in, you essentially pull 2 hydrogens out. Okay, so that's rule 5. That's multiple bonds. That's doubles and triples. Okay, so for rule 6, I'm going to draw something a little different because I think it'll better illustrate the point. So we're going to draw the molecule acetone. Acetone, 3 carbons. There's an oxygen there. You might notice that looks like fairly similar to the alcohol formula with 1 less carbon. But this is not an alcohol. This is a ketone. Again, we'll talk a lot more about the functional groups and what all that means a little bit later. But I'm going to draw 3 carbons. So 3 carbons looks kind of weird, right? Because it's just like, part of a triangle. But 1, 2, 3 carbons. In the case of acetone, it's a ketone, and so I've got a double bonded oxygen here. Okay, so that would be that's what that would look like. This is the proper way to draw this. And the reason that I say that that's the proper way is because this goes with rule 6. Once you draw a double bond, you need to keep the other bonds, other than the double bonds stay together, obviously, they're a double bond, but the other bonds need to be kept as far away from that central part where the double bond is as possible. What do I mean? Okay, so what do I mean is that it shouldn't look like this. Okay, this would be an incorrect way to draw that structure. Now, I mean, technically that is sort of correct in the sense of 1 carbon, 2 carbon, 3 carbon. There's my double bonded oxygen. Okay, that's fine. Well, remember back to Chem 1 that would obviously violate VSEPR theory, right? That these electron pairs that make up bonds, they're going to want to get as far away from each other as possible. Okay, they're a valence shell, electron pair, repulsion. So this shows that those bonds are getting as far away from that big mass of electrons in the double bond as possible. This doesn't. This shows, in fact, that they're attracted to it, and that is definitely not the case. Those electron pairs are repelled from each other. Okay, so just keep them separated as far as you can. That makes good logical sense. Okay, one more quick rule, and it's an obvious one. We've been talking about it multiple times, but I just want to make sure that you remember it. All right, so last rule, lucky rule number 7 when you're drawing line structures, carbons have to have 4 bonds. Okay, now there are exceptions to that. I've mentioned them multiple times already, even though you haven't seen a whole lot in class. If the formal charge is there on a carbon atom, it might not have 4 bonds. But that's not the norm, right? Most of the time, the carbons don't have a formal charge on them, in which case they have to have 4 bonds. It could be a double bond, which counts as 2, and then 2 singles. It could be a single bond to another carbon and then 3 hydrogens. Whatever, it has to have 4 bonds. I can't tell you how many times I've graded papers and someone has had a structure wrong for the really simple mistake of not checking to make sure that they drew their line structures to always give carbon 4 bonds. So please remember that last rule. That one's pretty elementary, I would say almost. But carbon's tetravalent. Make sure that you've got your 4 bonds unless you have a legitimate reason not to. And that will pop up, right? You're like, okay, there's a charge there, so maybe this one doesn't. Okay? This one has a lone pair on it, so it's only going to have 3. Okay? It's still going to be following the octet rule for the most part, but 4 bonds. All right? Thanks, kiddos.